So while we are gathering, first of all, note about the air conditioning. It has been brought to my attention that well, everybody felt that we have fluctuations. Apparently, it's right now very B-modal, either full heat or no heat, and neither version are good. So we'll try to alternate. So we divide the suffering until the technician comes and fixes the system. Michal, you want to share this? Okay. So we are going to start. We're going to have two short presentation where the poster session. Each poster will get 3 minutes to present the idea of the poster, so you can get primed up to what you want to ask them this evening. And we'll start with 3 of those, and then we'll have a panel, and then we'll have a break, and then the second, all the rest will be in the second session. So without further ado, sorry, you're
ready. So I want to present our framework for biological latent optimization for representation disentanglement of single-cell data.
You can introduce yourself.
Okay, that's a good idea. I'm Zoe Firan. I'm a PhD student working under the supervision of Dr. Mor Nitzan here at the Hebrew University. Okay, after my introduction, well, multiple attributes represent single cells, right? Every cell can be associated with the tissue of origin, its cell cycle stage, the cell type, or external perturbations that we may induce into the cell can shift its internal state. When we get single cell measurements, all of these properties are entangled into a single representation. So one ongoing endeavor is to disentangle this representation to really understand specific signals in the data. What can we do with this disentangled representation? We can obtain out of distribution predictions. We can identify gene trends, or we can perform some data manipulations. So while there have been many tools that are dedicated for a specific task, there's no one general framework that allows us also to disentangle and reconstruct the signal for any generic signal. So tools have been presented, for example, to decipher the cell cycle signal, or to really perform out of distribution predictions for perturbation data. But there's no one holistic framework. To this end, we present BioLord, which relies on LORD, which is a state-of-the-art model for disentanglement in image analysis, which was presented by Gabay et al. 2 years ago. So as input, we take multi-omic measurements of single cell along with labels for some known attributes. These can be the tissue of origin of the cells or the cell type, so those will be labels, discrete or continuous. Given this input, we obtain a compositional latent space representation of the data. So for each attribute, we learn a specific latent representation, and for all unknown attributes, we learn an additional representation. We do this by maximizing the completeness, the accuracy. There's a poster downstairs. Maximizing the accuracy. Okay, so there's a poster downstairs. I'll explain everything if you want to hear more later. We showcase our performance over the out of distribution prediction task for perturbation data set, and an additional data set, as I will elaborate downstairs in the poster session. I'm sorry, I'm not sending it. Okay, yeah. And I'll also take questions downstairs, not here.
Thank you very much. So I guess the instruction next time we do this will be that you have to keep some suspense going.
Yeah.
And present. But very good, very well otherwise. I'm sorry, I don't know how to pronounce your name. Piosh. Okay. So this is yours, right?
Yeah, but for some reason it's going down to.
You have to
Could you go back to the presentation thing? Down.
Oh, yeah, I'm not a Windows person.
On the 3 dots. On the 3 dots.
Oh, the left. Yeah. But I lost the. I couldn't see it.
Hi.
Okay.
Okay, great. Well, you can take the.
Okay, you can take it from.
Yeah.
Okay, I guess I'll just zoom in and try to show. I think this just. I think this should be fine. Okay. Hello everyone, my name is Piyush. I'm a first year PhD student in University of Edinburgh with Dr. Ajita Rajan. And today my topic is application of explainable AI to MHC class 1 presentation problem. In human body, it is important to identify and kill off the non-healthy cells. Non-healthy cells are identified by molecules called as MHC class 1 molecules, which basically samples peptides from cytosolic proteins and then they present it on the exterior of a cell, where then this another cell type called as CD8 positive cells comes and decides whether the cell needs to be killed off or not. This interaction between MHC molecule and peptide is essential for designing better vaccines and to understand conditions such as autoimmunity. Therefore, it's important to know whether a peptide can bind to MHC molecule. Now, with the advent of deep learning, there have been many models that have been proposed to do this task, where they take the peptide and the given HLA or MHC molecule and try to predict whether it can bind or not. However, there are two problems with that. One is that we don't know what patterns or what relations it's learning. Maybe it's some spurious correlations. And second, it doesn't work well for alleles or examples which are very rare. So to tackle that problem, we decided to apply explainable AI techniques, which essentially provides us feature importance to the given input when it makes a decision whether it's a binder or non-binder. In this research, what we did was we selected 4 of the top MHC class 1 classifiers, and we first evaluated their performance on an independent data set. Then we try to understand what explainable AI or explanations in this context mean, and then we decided to we try to apply this with various other explainable AI techniques. So through the evaluation of our independent data set, we found that MHC phobia is one of the top performer, and it's a convolutional neural network based. So the 4 that we decided were not only top performer but also had very different kind of architectures. Next, we wrap these MHC class 1 predictors with the explainable AI technique, and we generate what is called as a single explanation for one particular input. These are helpful to identify. So as you can see in this particular peptide, you can see some regions which are yellow, some regions which are not yellow, and like green or blue. So that means that it gives us importance of each position for the peptide. With this, we can identify why a particular peptide was classified as a binder and why it was classified as non-binder. However, one can aggregate these individual explanations and even create a motive to understand the overall trend of why, what are the factors that can help you to, what are the factors that help HLA molecule to bind to a particular peptide. Next, which XAI. So we decided to test other explainable AI techniques called as Lime and Deep Cover along with SHAP, and we tested them on 2 metrics, stability and similarity of the explanations. Thank you for listening.
If you all of this at the post.
Yeah. If you have any questions, please join me at the post.
And last for this session. Yeah.
Okay, whatever. What's up today?
Well, I'll just start. So I'm Gabriel. I'm working in a PhD student near the lab, working on liquid biopsies. So just in general, a view of cell-free DNA. So there are cells throughout the body that are dying constantly. Some have a normal turnover of cells, and then there's cases where a cell which is not supposed to die is dying. These cells that die release their DNA into the circulation, and it's cleared up rapidly in the liver after about half an hour. Now we know in the past decade or so that these cells maintain the nucleosome structure in the circulation, which means DNA is wrapped around histones are the proteins that condense the DNA, and they affect multiple aspects of the cell, including transcription. And when the DNA is released to the circulation, it's released as nucleosomes. So let's look at a cell from the liver. We could look at the gene of albumin. It's going to be open gene. It's going to be marked with chromatin marks of open promoter. But the same gene, if we look at the heart, where albumin is not expressed, is going to be closed, and it's going to have a histone mark of a closed promoter. Okay. This reaches circulation as nucleosomes, as I mentioned. We call that cell-free chromatin. And then the idea that we're using in our lab is to do chromatin immunoprecipitation, which basically we capture only the histones which carry the modification of an open promoter. So we end this part where we have now enrichment for open promoters in the cell-free DNA. And by the fact that we captured it, we know it's an open promoter, and by reading the sequence, we know what gene it was. And now we can basically try to go back and try to figure out where did this fragment of DNA, where did it come from, what tissue, and what genes were active in the tissue of origin. That's general about cell-free DNA. We applied this in the case of small cell lung cancer, which is a bad disease. And so it's a tumor that releases a lot of cell-free DNA to the circulation. And in the study we had also a matching biopsy for many of these cases. So we have a circulation where we see the cell-free DNA that's released to the plasma, and we want to compare it to their transcription in the liver itself that we got from the biopsy. Now, and it turns out that it's not so simple, and it's not a one-to-one match for several reasons, and I'm just going to go into one of them, and I'm going to end with that. So if we think of the biopsy, when we biopsy and we do RNA sequencing, we're basically sampling all the tumors that are inside, all the cells that are in the tumor cells, the immune cells, the stromal cells, but we don't know what of those cells gets to the circulation and in what rate. And there's an unknown mixture of other things. Whoever wants to hear more about this is welcome to come down to the poster session.
And I guess next time we have to reinforce when we mean one slide without animation, because so Gabriel gave the system on this. So we are going to get set up for the panel now. Yeah. So I'm going to turn off the screen and turn on the light, hopefully. Let's see if I can do it without destroying anything. Okay. Okay. Is that enough light, or we can do more light? Okay. All lights, okay. And how do we turn off the projector? Okay. And on your Scott?
Thank you very much.
Should we line up with our signs? I think it's easier to move the signs.
Yeah, we can move the signs.
No, they're both essentially the same.
Do you hear me well? Yes. Wonderful.
Talking over each other by having only one microphone. Two of them. Up to a constant.
So, after hearing a lot about the specifics of AI in healthcare, now is the time to have some reflection about the history and what was done, and what have you seen over the years in healthcare. So I'm very, very happy to be joined today by three leaders from the area of machine learning and AI, and I'll introduce you very, very shortly, because I thought how to provide a bio, just a highlight, and there are so many highlights that I was like, I'll just pick where you studied, and some things related.
They're all hiding behind the table, below the table.
So Professor Scott Kirkpatrick had graduate studies in physics in Princeton and in Harvard, and since then he was a professor and a visiting scholar at a wide range of leading universities across the globe, from UC Berkeley through École Normale Supérieure in Paris, Weizmann Institute and the Hebrew University in Israel, and many, many more places. Most important for me is that you were a leader at IBM Research as well, so that
I've even been in Haifa more than once.
as an IBMer, that's that's exciting. But probably before I came to IBM Israel, he was also okay. I would only mention, so I'm going to skip because I want to hear you guys. That you had many years of service as a member at NIPS Foundation, the second most influential conference in computer science according to all kinds of websites. Do you know what's the most influential one?
Who's the first?
Yeah. Somebody knows which one is the first? According to some websites that I checked last night, it's ICPR, the International Conference, ICVR, International Conference on...
Pattern? Yeah. P or B?
No. In imaging.
Is it vision? Is it the vision one?
Vision, CVPR. CVPR.
That makes sense.
Yeah, Shmuel keeps.
Computer vision.
CVPR was the first. Who says it's not that it's the first, Zoe?
Yeah, Shmuel said Shmuel is proud of that because he was one of the founders.
I think it had a 10-year advantage in starting earlier probably.
Okay, so that will come to the questions, right, of what happened with machine learning, AI, NIPS. And then I'm moving to Professor Yair Weiss, who graduated from MIT and conducted postdoctoral studies at UC Berkeley. You see that UC Berkeley connects also here. He is a professor at the School of Computer Science and Engineering at the Hebrew University and served as the head of the School of Computer Science here at the Hebrew University. And he served also as the program chair for NIPS in 2004 and general chair at NIPS 2005, and has served as a board member, I guess, ever? I don't know the exact. Now, for you, Professor Meir Friedman, who graduated from Stanford and conducted postdoctoral studies, guess where? UC Berkeley. He is a professor at the School of Computer Science and Engineering at the Hebrew University, and also a professor in the Alexander Silberman Institute of Life Sciences at the Faculty of Medicine.
And now I'm already Faculty of Medicine. Yeah.
Faculty of Medicine, okay, that's a full convergence.
Yeah.
Okay, he's the co-founder and co-coordinator of the interdisciplinary program for BSc in Computer Science and Computational Biology at the Hebrew University, which I thought might be interesting for this specific school, and obtained 3 times the ERC Advanced Grant, which is also an amazing, impressive achievement. But there were so many things to tell you. I want now to take the time and to hear from you about the first time you heard about AI, machine learning. Can you go back in time and remember where it was, what happened then, what was the definition of the research area back then, how do you define it today?
Okay, is this on? No. Now it is on, right? Yeah, okay.
Yes.
Well, there has definitely been an evolution in what people think of as machine learning, because and I'm ashamed to say that I've seen a remarkably large fraction of it. When I got started, when I finished my PhD, complex systems that didn't come in regular lattices had just become a thing, amorphous materials and stuff like that, and it became fashionable, if you wish to get tenure and move ahead, to think about things that were described by distributions, and not only mathematicians could worry about this. But machine learning back then was captured in a small number of textbooks, and it was filtering, pattern matching, pattern recognition. Generalization and describing softer things was definitely still in the future. fairly early in the game. I had a happy time working on spin glasses and other things that had statistics and that were in response to randomness. Things happened that would not have happened in a regular crystal or happened in a different way. So this was all perfectly happy stuff. But the opportunities that came our way, because we said we could deal with messy real data, as I started doing more applied things in IBM, included American Express coming to a small group that I was involved with that did early pattern recognition and saying, here's billions of dollars of transactions from the past year, and some of our customers don't pay their bills, and we end up losing money. Can you help us? And so we being people like Jerry Tesaro, who around that time was beating backgammon at its own game, built a 3-layer neural network, ever so slightly nonlinear, not very deep. And after messing around with training the network, we went back to American Express and said, if you had used our network last year, you would have saved $1 billion. And we described how it worked, and they looked a little befuddled, and they said, we can't use that. And they said, we can't use that for an entirely good reason, which is just as true today, and especially true in real-world environments away from finance. In finance, we've learned to if the computer says the stock is going to go up, by God, everybody buys it, and you end up every so often being misled, like with cryptocurrencies. But what happened to the American Express people that made them say that's all very nice, but we can't possibly use it back then, was that we had taken a simple process that would be described by a decision tree. If you meet this criterion, that's good. But if you fail the next criterion, we reduce your exposure. And if you fail the third criterion, we kick you out. And you can only get in by paying more money than you already owe to get, ahead of the game. Linear, sequential, human-type behavior would satisfy management. They furthermore said, well, if you have a mysterious computer that says, we suspect you're not going to pay for this diamond ring, and it's close to Christmas, it'll go through 2 people. At the store, the merchant will call American Express and say, why aren't you honoring this purchase? And the customer and the store really want to sell the diamond ring and have a nice Christmas. And the poor agent in the middle will say, well, our nonlinear neural network says, and it's all, and the guy says that you haven't paid for last month and you're not going to pay for next month. And the customer in the store will say, oh, the check is in the mail. And the result was, 20 years ago, this didn't fly. Well, now move forward to some of the other softer environments. The guy on the American Express end of the phone call, that's like the doctor. You want to give him advice that he has a good reason to trust. And the customer in the store who wants to walk out with his diamond ring, in many ways is like the patient. And all three of those characters exist to this day and in many different environments. So anyway, that's where I got started, and lots of stuff have happened since, but I'll turn it over to Yair.
So remind me the question.
When was the first time you heard about AI and machine learning, and how has it changed?
Okay, so that's a good question, because I think AI now means something totally different than it meant when I was a PhD student. So when I was a PhD student, when people asked me if I did AI, I would say no, I do not do AI. I do machine learning. And it's funny that in your question, they're synonymous. So AI, when I was in grad school, it meant...
2 different fraternities.
It meant kind of like, there was this acronym GOF AI, good old-fashioned AI. And it meant things like expert systems, search, complicated search heuristics, and that's not at all what we thought of ourselves as doing. So we were doing neural networks. That was what the field was called, and it had a lot more data. It was much more data-driven than old-fashioned AI, and it was much more about numbers and continuous numbers than about logic and symbols.
And like what Scott said, it was the first version of neural network, maybe not very deep, not explainable, and complex for people to adapt. Do you see the same challenges today, like in what you saw before?
Yeah, so I had a paper in 1999 in the Handbook of Neural Network Theory. A lot of the stuff is similar to what's done today. I don't think that has really changed. I think the main thing that's changed is computers have gotten much, much faster, and the amount of data, which is probably has exploded. So we would train our models at the time on, I don't know. I worked on one patient database, medical diagnosis, which was called QMR. I think it had 5 patients. At least the one that I worked on had, I think, five patients. I think that's the main thing that's changed. I think the words have changed. AI no longer means what it used to mean. And now what we call AI is what we used to call neural networks or machine learning, which is fine. And the other big change is really the computing and data, which have really exponentially grown.
Have the AI people died out, or have they merged with the machine learning?
No,
Yes.
I'll use this as a... So I met AI when I started my PhD, and I had to select the area, and what was called AI sounded to me the closest to what I wanted to do, although I didn't understand what was involved. And back then we had to do, I think they still do it at Stanford, you had to kind of do a qualifying exam. So you had to learn the whole field and do an exam to show that you understand what you're doing.
So still do?
I don't know.
People here doing PhD?
Well, I said in Stanford, I don't know. So
In the US, you'll see MIT does.
Yeah. So then I learned about AI and about expert system and what Yair called the good old fashioned, and some field that was near it that was called machine learning, and neural networks were mentioned in the, so we were the other companies. And I think learning properly I started doing only 3 or 4 years later. Paper that compared naive Bayes to other methods we invented, and this paper is highly cited for 2 reasons. One is showing that naive Bayes, which is a very simple classifier, is great, and people use it to say why they use naive Bayes, and other people use it to show why naive Bayes is not great, and there are other better methods. So when you if you write your paper properly, it will be cited for both sides of the aisle, and you're going to get both things. But then I learned about things that were done in the 60s in statistics, and one of the things that we learned is that we reinvented the wheel like the 3rd time. And so by the time we wrote it as a journal paper, we were citing work from early 60s that we thought we invented, and we discovered somebody else who invented it before us, and we both of us apparently reinvented the wheel. So, and I think that's a theme that's going to return in some of the next questions. But one last comment about the early days. I was then working on learning Bayesian networks, and one of the problems was, as Yair said, was the lack of data. And so we started a website to collect repositories of relevant data for networks, because there weren't that much data that came from the real world. And so today we are it sounds unfathomable to say that I'm lacking data. It falls on you from the air. Back then it was like a major limiting resource.
Very interesting. I didn't understand that it's part of a pattern, because also one of my first papers in AI was about DLR equations from physics, and to show that Parisi and others who analyze these equations on spin glass actually came up with algorithms for approximation that then reinvented by the AI community or machine learning community. So probably it's a repeated theme, that reinvention. So now comes the question, and that brings me back to my days when I moved beginning of the new century, somewhere there, to California, and people were talking about AI winter. And I didn't know what they were talking about, because for me it was only shiny and summer. So I'm wondering if you know more about if you know more about the different periods of AI winters and AI hypes, are there such things?
Well, there's been problems. There've been AI and machine learning and adapting computing, using computing to interact with the real world in useful ways, has always had two communities, which you can think of as people down on the bottom looking up and people on the top, floating high above the surface of the water, but thinking about what it must be like down there. And the evidence for this, one of the places where people trace the foundations of AI is to a meeting in Dartmouth in the 60s, I think, very early 60s, and Marvin Minsky was there, Bernie Woodrow was there, one of the first engineering-style machine learners. And it's great as a point of origin, but one of the people who organized it got quoted in an article I saw in an MIT popular journal recently, saying, you know, it ran for 2 or 3 months, and we thought everybody would get there and they would talk to each other for the whole time, but it turned out they didn't come at the same times, they weren't there the whole time, and they didn't talk to each other. And that element of people with different languages or people with different points of view having real trouble understanding those different points of view is a problem. Now, the AI winter question is the perception from the top that it's really getting hard to get your congressman to answer your phone call, or your favorite funding organization, NIH, NSF, etc., to create a wonderful new initiative out of which you can draw some thousands of dollars and support some dozens of graduate students. And those things come in waves, because even in the current day, the current thing in supporting cool research is to find a billionaire who realizes that he's got to put his billion that he just cashed in into something tax exempt, like a foundation, to do good things. And there are now organizations who help the sources of funds that are slowly replacing the NSF and the NIH to become quasi-governmental organizations causing good things to happen. Now, if it's a person causing a good thing to happen, he wants to see something like a disease cured on a reasonably short time scale. And so this means that it's going to be bumpy. On the contrary, I did a little piece of data gathering, which I'll share with you without putting up a slide. I looked at how many titles and how many pages were contributed by AAAI every year in their 40 years of existence, and to NIPS every year in their 35 years of existence. NIPS is monotonically increasing. You need a semi-log plot to see how it's going. AAAI, because it's been dominated by the elite perspective, has tended to get out beyond its skis a little more often. And therefore, they've had some ups and downs, but the two of them are basically semi-log partners in this progress of continued research.
I have a slightly different perspective than Scott. I think, and again, it's all about definitions. I think if you look at there are these two different research fields. One is the more data-driven one, and one is the more logic-driven one, and first principles-driven one. Let's call one old-fashioned AI and the other one machine learning. So I think usually when people talk about the AI winter, they talk about old-fashioned AI. And indeed, in the 70s, there was a great deal of promise, and then just it was hard to get those things to work. Again, in medicine, the story I've always been told is about expert systems. They just didn't work, even though a lot of money was invested in them. And the reason, at least that's what I was taught, is that they were not data-driven. And you look at the more data-driven approaches, like machine learning, those are the ones that are more.
I tend to disagree.
Yes, but that's
Oh,
fine.
that's gonna be very interesting.
So I think I mean, there was a phenomenon like AI winter. I think, and I think getting out of their skis. I like this term. Different communities tend to overpromise when things go well. And we don't talk about this, but machine translation, for example, was killed off as dead field and nobody will ever work on it. I don't remember when, in the 80s?
Oh, multiple times.
Multiple times. Because people did not get past something and they promised a lot and the funder said, okay, we don't need to invest in translating to English to Russian and backward if it doesn't work. And so the DARPA cut the funding at one point, and so those things oscillated. I think machine learning suffered from the same. We don't talk about the winter AI. When Rumelhart started with neural network, I think that was the first kind of use of those terms. There was a big hype, and then people realized it doesn't work and stopped using it. And then I think it reemerged at least 3 times before the current wave. The current wave is surprising because it doesn't collapse yet. People are promising the moon and delivering, which is impressive. But we have to remember that the natural human tendency to think that if something works, it will continue to work on other more complex things is. I guess that's what you call the people who are looking from above. I'm not sure, but.
Yeah, maybe I would say there's 2 graphs. Sorry, there's one that is more cyclical and there's one that is monotonically increasing. I think the one that's monotonically increasing, there are 2 of those. Those are Moore's law and data.
Yeah.
Those are really monotonically increasing, and that anything that can benefit from those 2 graphs will also continually improve. The other approach, which I think has its ups and downs, is one that's much more perhaps difficult.
Usually it's not denominated in dollars.
Wait. Before we get into the finance element of it, let me just, maybe you can say a few more words, because I'm not sure that everybody knows what you mean by the Moore law and the data growth, just to be a bit more explicit about the 2 trends that are clearly growing.
Yeah, so certainly computing power has grown exponentially for many years, and we hear about the death of Moore's law, but it continues.
It's still kicking.
It's still kicking. And that's a huge effect. I mean, really, it's hard for people to imagine when we were doing our PhDs how little compute we had compared to today. It's hard to imagine. And so I was doing computer vision. I worked on images that were very, very small and
64 bits.
Yeah,
64
so
pixels.
that I think that's one. And again, the number of data. We'll get to this soon, but some of my students now are working with this data set called Lion, which is 5 billion images.
So small?
Yes, we were working with a handful of images only 20 years ago. So I think those are examples of graphs that are monotonic. It just keeps increasing. The amount of data is going up, and the amount of compute is going up. The ones that are going up and down, I think, are related maybe to particular approaches to machine learning. So at one point, people thought that heuristics in search, that's what everyone should study, and that had at some point that was very hot topic to study, and then it became a not hot topic. Other areas, maybe genetic algorithms, fuzzy algorithms.
Let's not go there.
So yes, let's not go there.
But
So I think that's where and I totally agree, that's where you have this up
no,
and
but
down.
the same with boosting and SVM.
Yeah,
they have their
they have the ups and downs, but I think data and compute are the ones.
But it seems that
It isn't. I don't think it's ups and downs. I think any problem area proceeds by a new idea saturating, and then the next new idea passing it and saturating.
But there is a hype effect. I mean, if you think about the ups and downs, there is this deep learning has the promise to do everything, then it becomes foundation models, and then the over-promising, maybe like what happened with Galactica or other foundation models. The Galactica, you might know from Meta, Facebook, that went out and was said to create your own paper, and then people showed that it made, from MIT, there was a summary of how it made a paper about bears in space with references to people who talked about bears in space. So these kind of things, it's a big hype. And then you learn exactly what it can do, and then you actually, you move the boundaries of the capabilities of the humankind with these technologies. But sometimes there is a hype, right? Do you feel the hype?
One set of statements, the steady growth statements, have to do with the integral of what we've accomplished so far. And yes, indeed, it keeps piling up. Finance, excitement, headlines, that has to do with the derivative.
Spoken like a true physicist.
Yes, I agree about the derivatives part. Okay, we are now getting closer to medicine, because this is a school about how AI can get us better medicine from all kinds of perspectives. So how central were medical-driven use cases in the prioritization of problems in AI community? Are the solutions real and practical? Do you expect more to come soon? What's your view?
Well, this is well outside my field, but when I got started, just to emphasize how far we've come, 1 megabyte of information, a megapixel of display of that information, and a megahertz of computer speed was pretty good. And so all three of those are up by a factor of 1,000 in the present day. But the critical point was the data for medicine was not available when I got started. It has become available, even though there are terrible troubles. The reason Israel got vaccinated against the coronavirus is that we only have 4 healthcare facilities, healthcare networks. The United States has more or less 40 providers who all sit on separate bodies of data per state, and of course 50 states. Is that how many we have? I forget. Medical data has been the slowest to move from idiosyncratic and very, very local to global. Financial data and engineering information and geo data has been available ever since satellites went up. We've had geo data that deserves an interpretation. So medicine is probably the last to join the field.
So I think from classical AI, good old fashioned, medicine was always kind of a standing problem. I think much of the improvement in the area of research that I care about, which is dealing with probabilities, was driven by people from medicine, because while you can have an expert system that says fund or not fund a transaction, people who were talking about decision in healthcare wanted the odds and to weigh in the utilities, because they had utilities to weigh. And so the early Bayesian networks, for example, were done in the context of decision making. I think when you look at it today, it was very naive, because they claim they are doing better than doctors, but they had to have somebody look at the image and input a lot of features in order to be better than the doctor, and which meant that nobody will ever actually do it. But in their credit, it showed that the potential for doing decision making based on automated reasoning. And so I think I agree, Scott, that data from healthcare is much harder to get from other sources, but I think the problem was, in our face, and there's a whole field of medical AI-ish informatics that we may not meet every day, but a lot of advances came from there, actually. So I think medicine is a key problem to work on.
So I want to ask a follow-up question to you specifically, because I know you made a shift, right? You started with computer
I'm not an
science.
Example to anything. Yeah.
Not an example. You can give us your reasoning for the end of one, for your own, how you were drawn to this world, and what was the point that you realized that you are going to move to the Faculty of Medicine and not to stay a pure computer scientist? If it's okay to ask, you don't
Is
have
it
to
a
answer.
key that opens more doors?
No, it just
computer science position?
it's restlessness and learning to ask questions in another field and enjoying having to ask, not doing, instead of dealing with the same problem when trying to actually solve it, you move to ask other questions, and you learn a new set of skills, and so you can continue doing that. I moved to do experimental biology because I was collaborating with biologists, and you can ask why I did that. But and then at some point I started asking them why not do the experiment differently, and they said, so why don't you do it? And it's not exactly like that, but that's the gist of it. And moving to medicine was because we realized we can say something about humans, so you start talking with doctors because they are the clients on saying something about humans.
No, the patient is the client.
Well, depends, but I think there are three. If we want to talk about the clients in medicine, it's the healthcare provider, it's the doctor, and it's the patient.
And the payer?
Payer is the first one I mentioned.
Provider and payer?
Payer is,
Okay.
the system.
We have a lot more clients. You have the pharma, right, that you want to satisfy in their discoveries, and you have
but that's a different
a
playing
whole
field.
different story.
Yeah.
Yeah, thank you very much. Actually, Yair, I know that you are like, I will call it dancing with questions for medicine, doing it up and down sometimes. Is it the most appealing questions? Is it like more intriguing? Is it more challenging?
It's a good question. So I had a student, maybe that's what you're talking about, who did protein folding with machine learning
Chemistry.
20 years ago. I think, and I worked on Kriomar, which is this automatic medical diagnosis thing, which had 5 patients, as I mentioned. I should just say that there's an Israeli startup by the founders of Weiss, one of the founders of Weiss, who is redoing QMR. I don't know how well they're doing, but I saw they were in the marker recently. Yeah, I think for all of us, it's especially after COVID, we all understand that health is so important and interesting, and it's much more fun to work on than defense applications and so on. So I think I speak as someone who has never really thought of himself as doing medical research. I think anyone who looks from far away thinks of this as a fascinating topic and one that has great benefit to society. So in that sense, I think it's a very clear sell, both to students and to PIs who want to work on it. I think the downside, as Scott mentioned, is really the availability of data. Many machine learning researchers at the PhD level, first they have the data set, then they figure out the algorithm. That's just the way things are, and I think that puts medicine in a bad spot for the sort of people who are not 100%, don't think of themselves as medical researchers. It's much harder for someone to just play around with medical data and see what they want to do.
Yeah. Can I comment on that?
Of course.
So I agree. I mean, there is the failure of, well, the fallacy of I will save the humanities and cure cancer, and you have to beware of that. I think today we're in the age where there is a lot of data, and it's actually accessible under the right condition. The UK Biobank is one of the most famous example, but it's not the only example. It's for those who anybody here know what the UK Biobank is? Okay, so half of the people. So for the other half, it's a big UK, as the name suggests, effort to collect a lot of medical records data and actual assays, including fairly sophisticated assays on a cohort. I don't remember the last number, but it's in the millions, 500,000 or something.
500,000 today.
And so it's a very extensive data set, although by now it's you might think of it as small, but it allows people to start doing interesting data research on many interesting problems, and I think data is coming. We're trying to get 2 hospitals and 1 healthcare provider, HMO, to share data on a single research problem, and it's a nightmare. But just the technical and the legal, we didn't get to the machine learning yet because because of all the trouble in between, but we'll get there eventually.
There's a time frame. You have to make some progress in the time it takes a student to finish their degree.
There are many students, one after the other.
Well, yeah, no, this is still not at the student. This is still at the technical support level. I will not sacrifice a student if I don't see something come out of it. But I do think that. So for some of them, it's clear. But I think if we go back to Scott's original story about American Express, I think many of us, the computational people at least, we don't realize the complexity of the system we are entering, and sometimes that's good because being naive is the thing that allows you to ask a question that's and to show that something that's nobody thought about or nobody will ever use, even if it actually works and get them excited. But you also have to realize that if you'll build the best classifier for X, and even if it's better than all the human expert, getting it into actual use in the clinic has to go through a lot of stages that are not relevant to what you thought of as the core problem of doing the classification. And if you realize that and you accept that then you're less prone to be disappointed when you came up with and you show that it's really great and then why nobody is using it. Or worse, you made a startup that shows that and nobody is buying your product. That's even a worse situation to be in. So you have to realize the complexity of the system, which has to do with the payer, the doctor, the patient, how life look like when you are a doctor seeing 10 patients during 1 hour. All kind of things that we don't necessarily think about when we think about the classification algorithm.
I think there's another element to what you said. So there's the highly regulated area, the complexity of the incentive system, the lack of data availability. Yeah. I think there's another thing that I would like to hear your view on that. And I know you did you took the time to learn the whole new language. But in some way, the medical language is obscured. It's not like you have a task to separate dogs from cats, or you do finance, understanding who paid or didn't pay their taxes, or who would follow the guidance.
As a physicist, I think you have your own share of complicated things. I mean, any profession will have its complexities.
Well, you can always escape into dark matter and dark energy.
Yeah. No,
a real question is: do you feel that when you go to work on data from the medical domain, it's much more complicated to follow the lingo, the tasks, and that you need to do a collaboration if you didn't learn the whole story, you need to have a collaboration. Is it a bug or a feature, part of the story that you need to work with the experts of the field? I don't think it's the same, and I don't know, Scott, you have probably the most experience in all the many fields that you work. I don't think it's the same as medical and finance or other things.
Can I, since I'm holding the microphone, I think that the short answer in any application area, you have to deal with the experts, and at some point it gets complicated. Whether it's planes or banks or...
And you don't see any difference between the domains?
It's just that it's a very large domain, but let's go.
Well, this gets to something I've been worried about as I hear all the wonderful... machine learning has gotten into, maybe well out beyond its skis or may have run off the cliff but hasn't recognized it yet because we're trying so ambitious things. My experience in learning new languages is moving from the fairly supportive and insular world of theoretical solid-state physics into talking to engineers in laboratories. Laboratories have politics. Each laboratory has a internal standard of by how much they exaggerate what they claim they're going to do. You have to learn that. You have to learn everybody's favorite stories. You have to just get to know the people. And so I would say the languages are, the language learning is understanding the world in which the people who are trained to do the thing you're hoping to help, the world in which they come up and the beliefs that they've acquired in coming up through that world. But remember my third person, you know, the patient. And what I don't see happening yet, I was having this discussion earlier today. We have all sorts of ways of predicting things, and really neat things, so neat, so elaborate that we can't really test it all. And we only optimize for the unusual, the real breakthrough solution by having our machines fight each other. And what we're not doing yet is looking forward to see whether a solution was really achieved, whether the patients got well. And so there's a whole new level of technology I'm hoping to see, which focuses on the end result, which bores down to the end result.
So I really hope that tomorrow panel would be about these scientific discoveries that, if I get it right, is some of your end result, right? How you use technology to discover new things that would serve us.
Well, there's two places where I think that's extremely important. I'm starting to see some of my colleagues looking to solve scientific problems, like complex ones like turbulence or weather and things like that, by taking the shortcuts that machine learning has pointed out might be productive. So that's one thing. And you can ask whether the rain actually started when you said it would, or whether the storm was as strong as that. I had point 2 but in my head, but I expanded on the weather, and point 2 got driven away. It'll come back, but
yeah,
go ahead.
It went with the wind.
Yeah. But I mean, there is a real need to focus on the next stage, which is now that you've got some trust between data-based predictors and doctors, and because the patients in the past have always trusted the doctors, if the doctor has the right bearing and carriage and bedside manner. The next stage is going to be finding out if the things the doctors have decided that they will expound are really working, and then the patients can come back. We'll have a Consumer Reports on accuracy of your artificially intelligent doctor.
That would be
interesting. At that point, at the moment, this is just conventional statistics. But the discussion that I was kind of intrigued by, and I put back in here somewhere to revisit, is we now know how to generate enormous numbers of attractive and interesting hypotheses, but how do we know which ones are novel, as opposed to just whether they can be opposed or whether, we can make lots of good predictions which are conventional enough that they ought to work. And this is kind of an engineering tradition. An engineer who may have been trained as a mathematician to optimize things, to find the unique best solution, he goes to work for a company that makes stuff and sells it and pays the stockholders, and he discovers that the company doesn't care about the best solution. They want something that's good enough and soon enough to ship. And so we're really solving the good enough and soon enough to ship problem at the moment, and we shouldn't be convinced that that's the optimal or that's the unique new discovery.
Agree. That might get back to explainability, but we want to finish, but before to close with some quick questions to all of you. But before that, any question from you guys that you want to pose to this panel before we continue?
You can offer cookies.
Yeah. I think Lucas has a question.
It's something that has been addressed consistently throughout the panel already, but it seems to me that machine learning for healthcare is always a lot behind any other areas of research, in which maybe we don't need to have so much care with how we validate our results. like you throw a lot of models out there for computer vision, for example, and people are going to stick to whatever works, and you can test what works and what doesn't. How do we build a pipeline, or is there anything out there on how do we build a pipeline to validate our methods in the clinic, taking all these variables that you mentioned into account that are often, at least in my experience, not really taught, such as how the medical system itself works outside the specific problem that you're trying to solve with, let's say, quantifier.
So I think I want to divide the answer into two parts. So first of all, using the latest and greatest method is not always the best thing to do. I mean, we are really excited about it, but a year from now, we'll decide that, you know, gradient boosting was a mistake and we should do something else and whatever. I don't know what's the hype today. So sometimes simpler methods are more robust and they do. From the perspective of the application, being good enough is often good enough.
Good enough soon enough.
Yeah, yeah. So the fact that you're using linear regression doesn't mean that you're backward. It just means that linear regression is good enough to solve the problem. And so let's.
So just to understand, so your answer is maybe machine learning in healthcare is a bit beyond, but it's because they are doing the right thing. They are not looking for the hype. Is that the answer?
I think at any application, I used to use the analogy of hammer person versus a nails person. A nails person wants to get the nail in place. It doesn't care if the hammer is shiny or has the latest whistles and so on. If you're involved in inventing hammers, you really do care about that. So any application area will have that trend. I'm just saying it's not necessarily bad to use the latest and greatest method, but sometimes you have to prove to yourself that they really are much better. So I'm not sure if it's backward or just more cautious about the methods. Regarding the validation, I think that's a problem in medicine throughout, and if we talk about the future of medicine, there are two types of validation we can think of. One is for example, you can look backwards and say what the machine would have said and how does that match what we later discovered about the patient and so on. So you can do a lot of backward training. But the area where we're going to run into problems with AI or without AI is essentially, I think, in what we call, I don't have a good name, I'm open to suggestions, but a very informative decision making. So we're talking about medicine that will look at a particular patient and say, given the perspective of all that we know about that patient, we'll make a decision that is very different from somebody suffering a similar disease that has different issues. We call it sometimes personalized precision medicine, informed medicine, all kind of names. And AI comes in there as well. And from the perspective of so I'm taking a step back. The perspective of medicine, how you validate a treatment, a drug, a decision making is you take a cohort of patients and you try doing protocol A versus protocol B. And protocol A and B can be a placebo and a drug, or it can be, whether you give the chemo first and then do remove the tumor versus doing it the other way around. But you always do a randomized trial where you show your method is working. And once your method is precision and different for every person, I mean, are you testing the algorithm? Are you testing the algorithm on common cases? I mean,
well, you never could try both methods on one patient.
Well, yeah, and I think so. So medicine is going to run into that problem, and that's why today, there are trials for decision tree of depth 2 or 3. If the patient responds like that, we'll do this, and if not, we'll do that. But getting them to try a very complex decision-making process, regardless of whether AI is in there or not, is actually going to be a serious issue, and also an issue for us to say when do we know that our prediction makes sense, and where we think we're guessing in the wild because we really don't understand whether that combination of situation, our models or our predictors can really say something about which drug will work. So that's, I think, a big problem in the field that will come to bite us.
I have. I have a dream of evolving medical prescription, medical proposals. For example, in 18 months of dealing with the coronavirus, we managed to conclude here in Israel that the Pfizer vaccine administered twice, 3 weeks apart, to patients over 60 or over 50, or even including the pizza delivery guys who came in at the end of the day to take up the unused vaccine, did more good than harm. A one-bit decision based on 18 months and 100,000 patients. What I would like to see done is experimentation on a population, somewhat more similar to what we do in the spin glass derived world. We take many copies of a system and we study them at various temperatures, and we move information from copy to copy to move towards what approaches the desired behavior of the system. And we slowly anneal, and but at all times we break the system up in different ways. In machine learning statistics, this is called
simulated annealing.
No. I'm thinking that you chop the system up different ways and look at the data in many different ways. The point is, instead of a one-bit answer, wouldn't it be nice in epidemiology, with a proposed solution to a problem, to come out with a manifold of patient characteristics against which you had what seems to be a reasonably safe range of possible interventions? In other words, you come out with a functional solution rather than a one-bit answer.
So I think
so medical statistics, I think, is lagging way behind, because of the limitation, perhaps, of doctors explaining things to patients and to insurance companies that are going to pay for it.
There is another limit.
Okay.
I think most of the doctors learned that models that try to predict functional outcomes tend to break down. And so, as a field...
Are there examples that have failed?
I think medicine is full of situations where examples that now you teach them as this was a bad idea, but people thought they were doing better because they believed their treatment, and only when you did randomized trial you learned that resection, what's called radical resection, is not a good idea for cancer patients, or radical chemo. I mean, cancer is like the field of cancer has always the
pendulum, the non-medical pendulum.
Yeah.
That's
and when medicine moved to evidence-based medicine, where you did real trial and randomized trial, they're not perfect, but they actually, you started to see what really helps and what not. And that makes a lot of sense, but it runs against exactly what you want, which is generalization, which I also want, but how do you prove your generalization works? And if you do the kind of worst case analysis of theoretical machine learning, the numbers you need are not relevant to what we have. So you have to make a leap of faith, or have a very strong good prior, and that's the question.
Well, you're describing an optimization. You're describing an optimization that if we simply turn up the dial on one of the parts of the system for coming up with safe and effective medicine that we have today, it'll increase the cost in some other part of getting the data together beyond what's affordable. So somehow you have to turn up all these dials a little bit at a time, maintaining some confidence in the system.
I am not sure that we are going to solve this here.
Yeah.
I do know that tomorrow we have presentations about causal inference from large data sets, so it touches upon other approaches to slightly replace. So we have Andrew here and we have Michal here who would present tomorrow, and we will have more about this topic. We need to finish very soon, and I want to ask you like quick yes or no, or one word, 2 words answers. your real feeling about it. ChatGPT like foundation models are here to stay or a short-lived hype?
I think GPT is here to stay, ChatGPT is hype.
Same.
Same?
I think it's such a wonderful and friendly advance to have artificial systems that you can talk to, that we'll learn to live with them, and we will make them better in some gentle way.
Okay, so it's same to me. It's here, you would teach them, but it's not the same. It's not going to be the same technology.
No, they're going to get smarter.
Yeah. Okay, another one, quick. AI tech with a great performance as a medical support system, but without explanation. Boon or bane? AI tech with a great performance as a medical support system, but without explanation. Do you want your physician to use that, or you prefer not?
I would say no.
I say that the question is whether the physician will use them, and the answer probably will be no in the short term. I mean, like any other system, you have to come to trust it. So we trust today, I don't know, automated driving, almost. But 5 years ago, it would have been much
automatic
less.
planes we trust already.
Yeah. So I think you build your confidence. I mean, you don't really understand how your car managed to stick to the lane or give you a warning when you're about to crash someone, but you start believing it. Doctors will not switch to a system they cannot understand why it's recommending something that they wouldn't have thought of by themselves. So it's a bane because it will not be used.
I think developing trust is critical, and especially when there are multiple stages along the way. Cars that drive themselves and airplanes that fly themselves. I was an instrument-rated instructor when I left the U.S. and came over here, and I've recently been back in the U.S. a lot more, and trying to work with the current generation of navigators, and just being sure whether I understand what it is just trying to do and whether I gave it the instructions in the right form is a huge setback. And I don't trust them anymore, because I know how easily they can misinterpret my poorly expressed commands. So I think as we throw more automation into the system of delivering complex solutions to personal, social, economic problems, at first we think they're great, then they sometimes work, they sometimes don't. We start to learn what the weak spots were and what the blind spots are. And if we learn about the blind spots faster than we fix them, you have the situation of Teslas that everybody is scared of now, and for good reason. They stop in the middle of tunnels and cars crash into their rears. On the other hand, if the blind spots get cleared up fast enough, then we continue to trust them and don't spend as much time worrying about how they could possibly kill us as opposed to get us there.
Okay, so I would say you have the same answer.
I'm skeptical
For
too.
physicians or patients.
And I personally like to. I'm intrigued with why these things are doing all this stuff for me. So I'm more inclined to dig into why it made that decision than most practitioners might be.
Okay, I think we have to finish. We have more posters to hear about, but before that, you have here a very diverse team of people who might start a new project in AI, in medicine. What would be your last piece of advice from your experience and knowledge on how to do it right?
So I can just quote, we had in the faculty meeting, one of our students in our school sent a tweet to Jan LeCun asking him what advice he would give to a graduate student in machine learning, and I can just quote what Jan said. He said, "Don't be afraid, think of big ideas, don't try to improve performance on the benchmark by 1%. So that's also my advice to you.
I thought that's what NIPS did for 15 years.
That's what he did as well. That's not his advice.
Any other piece of advice for someone who is about to start a project?
I don't know. Everybody needs a combination of a vision, a goal, and a lot of experience and the willingness to get more of it about what really works.
I think we will leave it with that. I hope this energizes you for the next 5 days of discussion. Thanks a lot. Thank you very much.
Thank you.